I've been with Crate for about 2 years, and prior to that have worked like 25 years or so in the database industry, launching prior to Crate. Cloudant, going backwards in time, from most recent to longest ago, Cloudant, which IBM acquired, that was a hosted database as a service built on CouchDB. Prior to that, launched Vertica and VoltDB, Kaleido in the data warehousing space, Object Store going way back to object database days in the 90s. But I've been in the space for so long because I think just databases are cool. Big innovations in databases and allow us to breakthroughs in what we can do as software developers and really transform the way we live and learn and socialize and do business. So it's an exciting segment for me, and love being at Crate to continue that mission. Anyway, as I mentioned, today we're going to talk about machine data, or as we sometimes call it, things data, and where we really believe the next big growth opportunity in software engineering and certainly data management exists. And we're not alone in that opinion. Looking at something, Gartner, if you're familiar with them, industry analysts, their predictions are that in just 18 months, less than 2 years, about 50% of all new software being developed will relate to IoT in some way, okay? And really be processing machine-generated data. And machine-generated data can include things generated by factory machinery, IT networks and infrastructure for security analysis, automotive, smart vehicles, smart cities, mobile devices, and so on. So, and we'll go through some of those use cases now. But really, the upside to managing this data, it really is very high, right? So it's the data that's generated by these machines, these smart vehicles, the wearables, and even IT infrastructure. It's just the definitive record of what's happening, and the better you're able to understand that and find anomalies and find patterns of good and bad, the better able you are to optimize a customer experience, or the safety of your factory, or the production of your factory, or the profitability of your business, and or even uncover fraud in various forms. So there's a lot of value in harnessing this information, putting it to work. A couple of examples of those are just to give you an idea of the kinds of software we're going to be talking about today and the kind of data management workloads we're talking about. These are illustrated by a few Crate customers. SkyHigh Networks, which was just acquired by McAfee, cloud access security broker. So basically, the internet traffic for almost half of the Fortune 500 goes through Crate every day. But what they're doing is really looking at helping their customers flag or identify internet traffic from their businesses to dangerous sites. They keep a database of those, or uncovering shared credentials and other security risks and threats, and raising those to their customers. Again, in fairly real time. Another example in the industrial space is Alpla. You may not have heard of the company, but you've probably come in contact with their products every day. They make the bottles that our shampoo, our beverages, our motor oil, and all sorts of other things go into for brands like Unilever and L'Oreal, Procter & Gamble, Coca-Cola. But they're using, they're processing data generated by their factory machines to optimize productivity, plant productivity, and equipment efficiency and effectiveness, reduce resource utilization, and really also make their workforce a lot more manageable, right? Really not change the size of it, but help them in a way deal with turnover and things like that, and lower training costs and labor costs. And I'll go through this go through this use case in more detail later in the presentation. Zoomtobel and Tridonic, smart lighting, right? So lighting systems aren't just screwing a bulb anymore, right? These are every bulb or light in something like the Burj Khalifa or in every Sainsbury's store, every Office Max, is monitored. Is it on or off? Right color? How much energy is it using? Is it on in a room that's empty or full? So there's a lot of information now that can be collected about lighting systems, for example, to know to optimize energy utilization and efficiency and things like that. So again, another example of this use case. And then the last one, smart vehicles, where some of you may already have OBD2 devices in your cars to track location or to connect with a mobile app that tells you things about your car's health and integrity. Companies are doing these in fleets of vehicles, like ClickDrive, doing this with Singapore, all the taxis in Singapore, among others, but collecting data at a very high rate and allowing dispatchers to see and drivers to see if their car is about to break down before it does and requires towing, which raises their costs, or even worse, ends up causing an accident. Okay, so and also allow them to do things like analyze driver behavior or some more energy efficient drivers than others, and all sorts of feedback. So being able to collect this data, it's really helped companies like these improve safety, improve productivity, reduce waste, and increase energy efficiency and things like that. So if you're building software that looks like these, or you plan to, you're in the right place today. Now, what all of these have in common is really the database workloads, and this is really very typical of the new machine data workloads. When you're trying to collect information and analyze information about every step somebody takes, or every light bulb, every bottle made, every message sent in the network. We put it simply this way. You're really talking about a fire hose of complex data that needs to be queried in real time, and kind of bundled sometimes in the cloud, sometimes at the edge. And we define that fire hose as it can be millions of data points per second, sensor readings, which we see quite often. Certainly, tens of thousands. The complex data, right? Very often the messages coming from sensors are in JSON, variable structures, or you have many different types of sensors reporting data to you. So, how do you deal with all that, the variety of data that comes at you? Or it can be logs with a lot of unstructured text in there that you need to mine. And the queries themselves, we're talking very often about time series, text search, geospatial, because you want to know, not just what's happening, but where, why, and analyzing very large databases of historic data, but as well as analyzing what's really in the here and now, so that you can alert and control and monitor in real time. Okay, so if that sounds like your database workload, then here are your database choices, right? So this is kind of an old diagram from 451 Research, their attempt to map out the scores, or probably hundreds of different database management systems, not all of which on this slide are still around, and there have been new ones added since this was done in 2014. But it's still the best view to show just how crowded the database management system scene is, or landscape is. And as architects, it's hard to, it can be hard to choose. It's definitely challenging to keep aware of all the different options that are available, and then, matching the right one to the use case is always that's your work. But actually, in such a crowded database landscape, it's funny. There's one data realm that really isn't that crowded, and that's one of the reasons attracted me to CrateDB, and that's the machine data space. And historically, that's been dominated by a company or product called Splunk, right? Which, released probably around 10 or 15 years ago. Really made their way and became the de facto solution in enterprise companies for collecting and analyzing log data, right, and some event data as well. And more recently, Elasticsearch and the ELK stack, right, starting to challenge them as just an open source offering, which is a lot more economical than Splunk, which can be pretty expensive. But both of these are full stack solutions for collecting and analyzing really log data primarily, but some event data as well. They include software to collect the data, forwarders and indexers in Splunk, search engines, and also visualization, data visualization dashboards. Elastic, it's the Elasticsearch search engine, Logstash, which collects and stores the data, and Kibana for visualization. It's called the ELK stack sometimes, or Elasticsearch, I think Elasticsearch formerly. That's the acronym for those three components. Both of these also have sort of turnkey analytics and integrations set up for, and visualization set up for security analysis. That's really where they make most of their customer activity. So security, information, and event management types of applications, application monitoring, things like that. More recently, really within the last, say, 12 to 24 months, time series databases have caught fire, no pun intended there, with Prometheus being one of them. But these are really, again, designed for more metric-y data rather than logs, really performing very fast aggregations of time series data from IT and IT infrastructure, CPU, stats, disk utilization, things like that. A lot of systems monitoring data, and so on. Okay, but what is missing in all of those? Neither ELK nor Splunk support SQL, and in the time series space, a lot of the most popular don't support SQL either. But that's a problem, right, for the masses. But the reason why is that just historically, SQL's not a good fit for those requirements I mentioned earlier, right? The fire hose of data, complex queries, and real-time results. SQL, traditional SQL, the SQL Server, Oracle, MySQL, just a little too rigid. The schemas, tabular schemas, and relational schemas, also hard to scale them up to ingest tens of thousands or more data points per second and query those as the data is streaming in. Obviously the schemas are fairly rigid, so that if you have a new message format or new censored kind of data package format, you've got to change your schema and modify the database that way. So it's extra development work. By comparison, Splunk and the NoSQL alternatives meet these requirements really nicely. Right? They scale very easily, especially things like Elasticsearch and Cassandra. They can handle the complex data. They're really not they're schema-less or support dynamic schemas, and really can adjust their schema automatically based on what data starts to show up in the database, which allows you to integrate data more easily with a lot less development overhead. Then finally, with depending on the solution you use, you can answer these queries within seconds or milliseconds as the data is streaming in. Okay, but the fact that SQL isn't supported in this space, or really hasn't been very present in this space, is a challenge, right? So if you believe that Gartner, and within really months, that half of our new systems might face or might have to support data workloads like that, we're really going to be hamstrung or limited by the number of people who are number of developers who are skilled in those NoSQL solutions. And today, although it's a large number, it's still, although the number of people who can develop with those NoSQL solutions is large, it's still dwarfed by the number of SQL developers out there. So, our belief is that, if we're really going to enable this explosion of new IoT systems that transform the way we live and work and heal and connect, we're really going to have to enable the mass. Either the masses of SQL developers are going to have to switch, come up to speed on these NoSQL solutions, or we equip those masses with new SQL solutions that are able to address the machine data workload, and that's what we'll talk about today. Okay, and so here's what's happening in the SQL space. If you're following, new databases, you're hopefully you've heard of CrateDB, and others like say CockroachDB, which are new distributed SQL databases that are really built on top of NoSQL technologies that have been developed over the last several years. And by combining these two technologies and approaches together, you're really getting, you're really enhancing, the SQL we know and hopefully love with the scalability, the ease of scalability, the flexibility of being able to handle a lot of different data structures, and even, query and data that's being ingested in the database, the same streaming data that we've kind of come to know with and appreciate in the NoSQL realm. Okay, so what does that mean? Like, what does CrateDB look like under the hood then? So looking at this diagram of the different sort of things that make up CrateDB, which is a distributed SQL database, open source. The stuff in blue are the things that we have engineered. So we really have created our own distributed SQL database engine. And instead of using traditional relational database storage and indexing underneath all of that, we decided to borrow some code from other open source projects, notably Lucene and Elasticsearch. So under the covers, Crate uses Lucene for storage and indexing, and is actually storing every row as a JSON document. And we use some code from the Elasticsearch project to do the clustering in CrateDB. So if you have experience with either Lucene or Elasticsearch, you're going to find a lot of Crate behavior very familiar, especially with the way it scales and works in a distributed environment. And if you're familiar with SQL, you'll obviously find Crate very familiar as well. It supports ANSI 92 SQL and a lot of the SQL 99 spec as well. Okay. In addition to combining, building SQL on top of this NoSQL foundation, there are some other things that we do in CrateDB in the SQL layer that make it such a good fit for this the machine data space. And so the things that really help us and you, deal with that fire hose of complex data and query it in real time are the following. Number one, distributed processing. So the workload, querying, ingesting is split across multiple inexpensive servers. Right? So if you need to double the throughput or performance or the amount of data Crate is handling, you just double the number of computers or nodes, which can be virtual or containers, VMs, physical hardware, to do that. Okay, without really interrupting the operation of your database. Actually, the second thing we do, I'm just going clockwise around this cloud here, is columnar caches. Okay, so if you're familiar with analytic databases like Vertica, Greenplum, or even Cassandra in the NoSQL space, you may have heard of columnar and columnar indexing, which is something that makes database querying go much faster. Crate actually caches its columnar indexes in memory, which is something it inherits in part from Lucene. And but this provides very, very fast aggregation and selection of data when processing queries. And this is really what helps give Crate its real-time and in-memory query performance capabilities. Underneath that, Crate is we also support this notion of dynamic schema. So if you're in Crate, you can use your plain old create table statement in Crate and give it a bunch of fields and very traditional data definition language using SQL. So if you create a table with 10 columns in it, and it's inserting data, happily with those 10 columns, and all of a sudden an insert statement shows up with an 11th column. Crate can be configured to do one of two things. Firstly, it can operate like any other SQL database and just throw an error and say, there's a column I don't recognize. Or secondly, it can kind of relax and just say, okay, I'm just going to assume you're adding a new column to the table, and we'll just add that there. So very much like a NoSQL database. So if you have, so in the case of Alpla, which I'll talk about later, where they had 900 different types of sensor messages, it actually enabled them to store all of their all these different structures in the same table, which ended up providing much faster query performance than storing those in 900 different SQL Server tables. Okay, so this dynamic schema gives you the ability to really handle a lot of different data structures, or even data structures that change over time without a lot of extra development. And then lastly, Crate cloud native architecture. It's a shared nothing architecture. So if you're building, you're using container platforms to, for example, to deploy and orchestrate, scale your software, you can include Crate with those. Crate runs as a collection of containers and can be orchestrated and scaled and administered through Docker and Kubernetes and things like that. So again, great in shared nothing environments. Okay, and like I said, Crate is SQL. So if you have experience using a SQL database, you know Crate. Okay, we support the ANSI SQL 92. We implement that, so all the joins and kind of relational things. There are a few things we don't do, and you rarely see in distributed databases, but stored procedures, triggers, things like that aren't supported, but otherwise you're good to go. Support a lot of the SQL 99 stuff as well. And again, this, compared to NoSQL databases, it really gives you, a lot of the, like I said, the ability to, handle high velocity streams of data, deal with complex data structures and queries, time series, geospatial, and things like that, and just has the added benefit of being SQL, which probably everybody in your organization has experience with and knows, and what the lion's share of different tools your business people use, support reporting tools and data movement, data integration, data pipelining, and so on. Just easy to fit Crate into your organization and start going and deal with these machine data requirements. Okay, we talk about performance a little bit. Crate is just a couple of benchmarks here. Crate scales linearly, right? It's really designed to do that. It's the benefit of the shared nothing architecture, really nothing that's gating the performance of the cluster except the size of the cluster itself. And that top graph shows that in a machine data, basically time series, sensor readings, time series queries on sensor readings, several hundred, so 300 million rows of data. As we doubled the size of the cluster from 3 to 6 to 12 to 24 nodes, the query throughput, the number of queries Crate was able to process every second, scaled pretty linearly with that, just around doubling with each doubling of the cluster. So very predictable performance, allows you to plan your cluster and how much computing and database management processing power you'll need to handle your workload. If we compare that to traditional SQL like Postgres, also in a distributed environment, the Crate will handle these queries. Again, the query throughput and performance about up to 30 times faster, depending on the type of query. But overall, and also running on hardware configuration that costs 30% less. So I think that comes to about a 33x increase in price performance, better price performance for Crate compared to Postgres in that example. And then lastly, looking at a time series database, InfluxDB. The time series databases are super fast at collecting metrics data and showing aggregations and graphs of that in real time. The challenge with those usually is not so much with performance, but it's getting them to do more. They're very single purpose, so they can tell you what's happening when, but if you want to understand why, as you learn those things, that they can be quite hard to extend and to do things like log analytics or to add geo positioning and things like that, where Crate, you just join. It's a relational database, so it's easy to extend the database with new information. And performance-wise, Crate really shines against Influx, at least, when we look at putting the database under load. And if you're a company like Sky High Networks that has a lot of users with dashboards open, looking at their security data, you're supporting a large customer base. Crate works very well in multi-user environments where you have a lot of concurrent querying happening at the same time. About 7 times more higher throughput as the or better as the number of concurrent queries increases. Okay, as I mentioned, the real nice thing about having a SQL solution here is interoperability. So the ability to choose your front end, to choose your data movement, data pipelining, right, around the SQL database. So anything that supports SQL, JDBC, or the Postgres wire protocol, or even REST interface can connect with Crate on either side of Crate. Elastic, Splunk, both have offered turnkey stacks from data collection, data indexing and search, data visualization. It's really started with Splunk, back when they were launching. In the early days of Splunk, it was just no SQL, and the idea of using something other than SQL was, people are less comfortable with that then as they are today. But just to make the product easier for people to adopt and use, they provided their full stack there, so that people didn't have to try and integrate Splunk with all the various front ends and data movement ETL solutions that are in use today. So again, nice freedom to build your own machine data stack in Crate. The other important interoperability thing here is people, right? So it allows people with to move onto or onto a CrateDB project or a machine data project and be productive much sooner, because there's really very little learning curve for them if they already know SQL, unlike Elastic or Splunk, where there is a learning curve and it makes hiring and reassigning technical people on these projects a little more challenging, and involves some productivity losses. They have to climb those curves. Okay, so in Crate's case, what is that machine data stack look like a lot of times? I'll start to get into implementations of Crate now. The originators of data will often send data to Crate directly in an MQTT, sort of following using the MQTT protocol or some other format. They may or may not use something like Spark to enrich that data before it ends up in the database, and may or may not use Spark on the other side of Crate to enrich the data before it goes into visualization, which is very often something like Grafana. But the nice thing here is it gives you the ability to create an open source stack. So with Crate, Spark, Kafka to handle the pipelining of all of this, and open source front ends like Grafana, you can have a very economical machine data stack. When you compare it to the cost of something like Splunk. Okay, and so in the physical world, these often are very distributed. You'll have Crate can be running on premises or even in device. The Crate database is written in Java, so it can run anywhere. Most of the in-device implementations or stories about Crate have been today mostly from hobbyists, but they do pop up with their articles about what they did with Crate on Intel NUCs and Raspberry Pis and things like that. So when we see Crate implemented in a kind of edge and cloud environment like it is at Outblow or ZoomTotal, it's implemented on in remote factories or buildings in very kind of traditional racks or servers, and will communicate data centrally to a cloud, either the customer's hosted cloud, or we can private cloud, or be on a public cloud like Amazon or Azure, or both. Okay, so some of the things in Crate that features in Crate that help you connect, make building your stack even easier are a new MQTT ingestion framework in Crate, and we're extending this to Kafka as well. But in Crate, what you can do if you're familiar with MQTT, which is a protocol for transmitting messages from systems, and it's widely used in in applications that use sensor data. And it basically, here's it's a publish and subscribe protocol, and what we allow you to do in CrateDB is to subscribe to an MQTT topic by telling Crate to listen for a specific topic, and also to what to do when it hears, quote unquote, a message on that topic, and that those are really just a configuration instructions that tell Crate how to map the data in the payload for that message into columns in a table in Crate. So if you're not doing any pre-processing of the data, if it's just straight MQTT messages into CrateDB, this is really interesting to people because it allows you to simplify your architecture and lower the cost of your system. It can eliminate, by eliminating message queuing software like RabbitMQ and things like that. Which were really designed 15 years ago to help support this kind of data workload with backend databases that couldn't be counted on to ingest, thousands and thousands of messages per second, or couldn't be counted on to be running 24/7. But today's distributed databases like Crate and others really don't face those issues. So it's starting to, in our opinion, starting to make that kind of middleware, the message queuing, a little bit obsolete. We also, Crate is an output target for Telegraf, which is an open source data collection software product, really more oriented towards time series data, but supports dozens of different data source formats, and you can use that again to, as well as a lot of open source data pipelining tools like Node-RED and others to transmit data into CrateDB. Okay, and the last integration we just completed was a Prometheus integration. If you're familiar with Prometheus, very popular in systems monitoring. It's an in-memory single node time series solution that implements a remote reader and writer interface. So for its customers or users that want to store more than a few days or maybe even more than a few weeks of data and in long-term time series storage, they can Crate supports their remote read and write interface so that applications that are like Docker, for example, that come out of the box ready to send metrics to and event data to Prometheus can use those to have that data sent to Crate, where you can store years worth or data from very, very large systems and analyze it with SQL. So again, just making kind of the merging of SQL and non-SQL data sources easier for everybody. Okay. All right, I'm going to go into a little bit more deeply now. So what does the SQL look like, and what does the data look like when we're talking about CrateDB? And I'm going to go through use one of our customers' stories to illustrate this. Again, if you have any questions, feel free to enter those into the questions box there. So just as a reminder, so Alpla, it's a global manufacturer of plastic packaging products, right? So they make the bottles for Coke and Procter & Gamble detergent, shampoos, and things like that. And their big idea was to take the data that their factory machines were generating. So they have 1,500 production lines in, I think, 170 factories around the world. Those production lines are already sensored up. They've had sensors for years. The data from those sensors measure things like weight, bottle shape. A lot of them are visual and video and all sorts of things. 900 different types of measurements. They've been just really used by the machines themselves over the years to really just to kick defects out of the manufacturing process as things go along. But Alpla had this idea, and sometimes that data can be used by people to debug things or kind of do retros on equipment failures and stuff like that. And but the big idea there was, like, why don't we take that data and put it in front of machine operators, right? These experts, and so that they can become better informed and tune the machinery in such a way that it's operating at peak efficiency and effectiveness, which lowers their basically increases their productivity and profitability, and also there's no reason why we can take that data and put it in the cloud so that we can centralize these machine data operators. They don't have to be on the factory floor 24 hours a day. And this made hiring and labor management a lot easier for Alpla. They have to make their bottles pretty close to where the stuff that goes in the bottles is made. So if you're talking about very high-end production equipment being operated in rural parts of countries, where labor is less expensive, it really helps with hiring and turnover, which can be pretty high, and really reduce the amount of training and skill that the people on the factory floors require. It's still a skilled job, but it's not like they need to they don't need to be top experts. What they can do is put this centralize those experts and connect them with the people on the factory floor to step them through repairs and tuning and stuff if something extraordinary is happening. Okay, so the data that we're talking about is JSON data. As I mentioned, it's like 900 different types of sensors on each production line. So we're talking about over 1 million different sensors in the company, and a lot of different message formats. And again, the goal here was to create a real-time dashboard that there's kind of mission control could use to monitor factory efficiency. Okay, and here's a picture of mission control, right? So this is where those experts are working, and the dashboards they're all looking at, you know, they're looking at a bunch of different factories, and within those, a bunch of even more production lines, but really, you know, allows them to reduce the operational expert to production line ratio, which is more economic. And as you can see in the two pictures connected by the red arrow, the experts are connected to people on the factory floor through some pretty cool technologies. One is the, you know, not too surprising, but the tablet with the, hey, you know, check, you know, setting blah 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 on, you know, a certain machine, which they can go do. But for things that are more complex, like you know, repairs and things, the mission control are connected to the factory floor. The factory floor people wear Microsoft HoloLenses, which are really, really great interfaces to allow the two of them, these two sort of people to work together on repairs. The person in mission control can see exactly what the wearer of the HoloLens is looking at as they're opening up machines and replacing parts, and they can even annotate and, you know, draw arrows and stuff like that on the person's field of vision to you know, make it clear what they're talking about. So really fascinating, you know, kind of labor and factory case study, really enabled by this putting machine data to work. The implementation of that, right? So they're using RabbitMQ to pull data from the machines. They're actually doing this on the factory floor and in the cloud. This is the version of what's going on in the cloud, but they run all this on Docker, right? So all the data enrichment, data loading, the database itself, CrateDB, visualization, all of this is running on and scaled with Docker in the cloud and on factory floors. Okay. In addition to the metrics data they're pulling in, they also store annotations and things like that. So when certain things go right or wrong, the mission control and factory floor people can add notations to the database that indicate why something may have happened or why not. That's very important to them, so that they can, they're a learning organization, and they want to make sure that they're not making the same mistakes twice, or that they're repeating successes, you know, and scaling those out. Okay, so I showed you what the JSON data look like. Here's what the data looks like in CrateDB. This is just our admin UI, and where they've just selected certain events from the metrics database where they're looking at for downtime, okay, ordered by TS or timestamp. And what you can see here is, you know, Crate's, again, kind of its NoSQL roots or foundation really allow it to handle things like arrays of data and nested data like JSON objects really comfortably. So you're seeing there, like machine as an object, this would be a JSON object, and you can query any one of those JSON fields. We're not doing it in this example, but they're all available to you. And so the full text search in Crate, we inherit all that from Lucene. Geospatial querying as well. Also, Lucene's got great geospatial indexing and querying. Excuse me. Also surfaced in Crate. So great for vehicle tracking, as well as you know, full text search, log search, things like that. And again, this is all visualized in Grafana in their case, and plus some other, I think, Zeppelin as well for now. But they're, yeah, so again, their choice of stack, and this is a really nice fit for Alpla. One of the main reasons was because they had tried to build this on Microsoft SQL Server. They're a you know, multi-billion-dollar organization, big Windows and Microsoft customer. And problem was that SQL Server, again, they were storing 900 different message structures, so that obviously 900 different tables, and trying to build dashboards that are querying 900 different tables in SQL Server is, you know, starts to get you away from real time. So it was taking around 3 to 5 minutes for each of the charts in the dashboard to refresh. And when you've got a dashboard containing 12 to 20 different charts, that's really not real time. You're talking about half hour to an hour to refresh. So they took a look at CrateDB, which could meet those performance requirements, got all those queries down into sub-second range. And what was really awesome from their standpoint was they didn't have to change a lot of code or queries because it was just SQL. You just move the data over, and the queries they already had were, with a few exceptions, just ran very easily. And it's really allowed them to get this implemented really within just a few months. Okay. So just to wrap up, so we're really, get ready for the new machine data requirements if you're not facing them already. Again, that fire hose of complex data in real time. The good news is if you've got a lot of SQL developers or a lot of software and tools or customers that that support SQL as a data access interface, the great news is that SQL's coming back to the rescue, right? With new database architectures like CrateDB that really give you the same, the scalability, the performance, and dynamic data handling that we kind of come to expect from NoSQL databases, but with the ease of use and learning curve and integration that SQL provides. So overall, you get much better economics and faster development in some cases. So where does that leave Splunk and Elk Stack or Elastic? Some of those still great solutions. I think you can afford Splunk, and you really need something that's more turnkey with visualizations and analytics and data connectors that are set up to really be a turnkey security analytics solution. Splunk's awesome for that. But if you're doing, you're really going to be developing your own or embedding database into a commercial solution, Crate's probably a better way to go. Just the open source nature, open source economics, and familiarity and ease that SQL provides. Okay. So if you want more info, I invite you to go to Crate.io. You can start using Crate, download it, run it anywhere.